In this video, we're going to look at delta G, which is Gibbs Free Energy. So we've talked about whether reactions are spontaneous or not. Spontaneous meaning without outside intervention. And we've already seen that spontaneous reactions tend to increase the entropy of the universe. So things tend to be more spontaneous if delta S is increasing or positive. And things tend to be more spontaneous also in terms of enthalpy or delta H if they're going in the exothermic direction, if delta H is negative, because that direction would have the lower activation energy. But what's the deal with spontaneous reactions that happen without outside intervention, but that are endothermic? Or what about an exothermic reaction, but it decreases entropy, yet we still know what occurs? So there's these two factors, enthalpy and entropy, that drive whether a reaction is spontaneous, and we can put them together in this equation to calculate something that we call delta G, Gibbs free energy. So if you look at your AP Chem formula sheet, you'll see that this equation's on your formula sheet. Delta G is equal to delta H minus T delta S. T being the temperature and it being the absolute temperature. So if you remember when we were doing delta S and we were calculating values, delta S was typically in joules per Kelvin. And that's why we're multiplying it by T so that the kelvins cancel out into a unit of energy. And it makes sense that there's a T next to delta S because the entropy is going to depend on the temperature. Remember we said the higher the temperature, the greater the entropy because you'd have more dispersed matter or energy. So if you end up plugging into this equation and calculating delta G, you can figure out if the reaction is spontaneous. If delta G is negative, or less than 0, which means the same thing, then you have a spontaneous reaction. It will proceed in the forward direction. We're not saying it's going to happen fast. We're not saying it's going to happen slow, but at some point it will proceed in the forward direction. Okay. Delta G is negative. Again, it means the reaction's spontaneous in the forward direction. If you get that delta G is positive, the reaction will be spontaneous but in the reverse direction, meaning it will not go forward. But if you happen to start with products, it would go in the reverse direction and turn back into reactants. So delta G being positive, not spontaneous, will not go forward. And if you get that delta G is actually equal to 0, the reaction's at equilibrium. And what does equilibrium mean? It means the rates of your forward and the reverse reaction are the same. The forward and reverse reactions are occurring at the same rate. And we'll eventually do a whole chapter on equilibrium. Okay. So again, we can calculate delta G and notice whether or not it's spontaneous. Whether or not delta G is positive or negative is going to depend on both enthalpy and entropy. Those are the two factors that are going to affect spontaneity. We said that typically we want a negative delta H and a positive delta S, but we don't have to have that to be spontaneous, and we're going to look at that in a moment. Now, unit alert. So since we're subtracting these two things, anytime you're adding or subtracting, you want to make sure you're in the same units. We said delta H is typically kilojoules per mole, but delta S is typically joules per mole Kelvin. By multiplying by temperature, kelvins cancel out, but notice that the energy unit is different. One's in joules, one's in kilojoules. So you're going to have to change one of them, delta S or delta H, from joules to kilojoules or kilojoules to joules. Usually I see them asking for delta G in kilojoules, so you'll always see me typically changing delta S from units of joules to kilojoules. Remember, there's 1,000 joules in 1 kilojoule. Okay. Remember, too, that delta G is only giving us information about whether or not the reaction will proceed forward. It does not give us any information about how fast this is happening, only or whether or not the reaction would happen. We'll get to a whole chapter on kinetics, which is rates of reaction. Historically, this word spontaneous has been used to describe reactions where delta G is negative, that will proceed in the forward direction. So the AP said, hey, this is a little confusing because the word spontaneous to me means immediate and kind of implies that it's happening fast. So they've kind of changed spontaneous into the word thermodynamically favorable instead, to avoid any kind of misunderstanding that this is happening quickly. We only want it to mean that this is happening like without outside intervention. So the phrase thermodynamically favorable or thermodynamically favored means that products are favored and the reaction proceeds forward. So if delta G is negative, the reaction is thermodynamically favorable and proceeds forward. So delta G, is less than 0 or negative. The process is thermodynamically favorable and it favors the products. It's going to go in the forward direction. And if you get that delta G is greater than 0 or positive, the process is thermodynamically unfavorable because it favors the reactants. It will not proceed in the forward direction. So thermodynamically favorable is one of those key terms that they love to use on the AP and that they like to see in a free response question as your response. Let's take a moment and practice using this equation. So here are some heats of formation for each of these species. Here are some molar entropies for each of these species, and you have this reaction. I want you to calculate delta H, delta S, and delta G, and after doing that, tell me whether or not the reaction is thermodynamically favorable, which is a synonym for spontaneous. Take a moment, pause the video, and then check your work. Okay, so we can calculate delta H for the overall reaction by using the heats of formation and doing the sum of the products minus the sum of the reactants. And just make sure to remember you're multiplying by the coefficients in front. They just all happen to be 1. So here's my products, here's my reactant, and just multiplying them each by 1 and showing that my final unit is kilojoules, or if you want to put kilojoules per mole. Some people think that by multiplying by the coefficient, the moles would cancel out and my overall unit would be kilojoules, but if you put kilojoules per mole, that's totally fine. Notice that my delta H overall is positive. This is an endothermic reaction. Okay, so let's calculate delta S next, and I can do that by using the molar entropies, and again doing products minus reactants times their coefficient. Okay, right now delta H, again, I said is positive. This is not technically super favorable, but we'll see what happens with delta S and how that will affect delta G. So, and I'm just keeping tally of my delta H up here. Don't forget that this little degree sign means standard state. That means 25 degrees Celsius, 1 atm, or 1 molar concentrations of aqueous solutions. So delta S, here we go, products minus reactants, but using the delta S's. And here I get a positive value, 108.7, and my units are joules per Kelvin. Don't lose that Kelvin, and notice that kilojoules and joules are different units of energy. I'm going to have to take care of that when I plug into delta G. Notice that delta S is more favorable. It is a positive value. So let's see how this is all going to impact delta G. And I'm going to convert delta S into kilojoules per Kelvin right away by dividing by 1,000 so that my units of delta H and delta S match. So now when I plug into delta G, okay, if I plug into delta G, first turn your temperature into Kelvin because we want the 2 kelvins to cancel out. So that's a common mistake I see, people forgetting to put in the temperature in Kelvin. And when I plug in, I get that delta G is a negative value. So if delta G is negative, it's thermodynamically favorable. If delta G is positive, it's thermodynamically unfavorable. Since delta G is negative, this is a thermodynamically favorable reaction. It is spontaneous. It will proceed in the forward direction. And it makes sense. If I dissolve this solid in solution, I am likely to get a negative delta G because this is known to happen. Okay, so let's just talk about the signs of delta H and delta S. If delta H is negative and delta S is positive, would the reaction be thermodynamically favored? Well, if delta H is negative and I'm subtracting from it a positive value, I am always going to get a negative delta H. I'm always going to get a negative delta G. So I am always going to get a thermodynamically favorable reaction if I have an exothermic reaction, delta H is negative, and I have an increase in entropy, delta S is positive. And that's what we said were those 2 factors that are most favorable. So it makes sense. Anytime delta H is negative, delta S is positive, I'm going to have a thermodynamically favorable reaction no matter what the temperature is. If I have a negative number and I subtract from it something positive, I'm always going to get a negative number no matter what the temperature is. And remember, temperature is being plugged in an absolute temperature, so I'll never get a negative temperature here. It's always 0 and up, okay? let's look at the opposite. If delta H is positive and I subtract from it a delta S that's negative, okay, I start with a positive number and I'm always subtracting a negative number. The two negatives would cancel out and I get something positive. I'm always going to get a positive number. So delta G is always going to be positive if I have an endothermic reaction and entropy is decreasing. So this is never ever favored no matter what the temperature is. So we should know that delta H being negative, delta S is positive is always favorable. And the opposite is never favorable. There's no need to calculate or even think about temperature. Now let's look at a condition where both delta H and delta S are negative. If both of them are negative, taking a negative number to start with and subtracting something negative, well, maybe I'll get something negative or maybe I'll get something positive. It actually all depends on the temperature. So if I have a low temperature, then if I'm taking this negative and subtracting T delta S, then I will get a negative delta G if the temperature is very low. But if I take this negative and subtract from it T delta S where T gets really large, then that's actually going to change it positive. So if I see negative, negative, it's only going to be favorable at low temperature. Sometimes we say this is enthalpy driven because the delta H term has to dominate. It has to be larger than the T delta S term so that delta G is overall negative. And in the opposite situation, positive, positive, this is only going to give me a negative delta G if I have a very high temperature. So at high temperatures, okay, T delta S is going to dominate, and I'm subtracting minus a positive number is going to give me a negative value for delta G. So you can think of it logically how I was talking about the signs, but if you don't like thinking of it logically, just kind of memorize this. If I have negative, positive, delta H negative, delta S positive, always thermodynamically favorable. The opposite, never thermodynamically favorable. Two negatives, only favorable at low temperatures. Negatives, think low, that kind of makes sense. Positives, both positive, only going to be favorable at high temperatures. Okay, so as I said, anytime you have your favorable conditions, delta H being less than 0 or negative, delta S being positive, there's no need to even calculate delta G. There's no need to plug into this equation. You know automatically delta G has to be negative. It's thermodynamically favorable. It will go forward. Okay, and hey, this is why we say reactions tend to go toward lower energy, negative delta H, exothermic, and higher entropy, positive delta S. And the opposite, you should again know the unfavorable conditions. Again, there's no need to plug into delta G to see that it would be positive. If you see delta H is positive, delta S is negative, you're always going to get a positive delta G. Let's try some examples. Take a moment, give this one a shot, and then we'll go over it. Okay, the reaction indicated above is non-spontaneous at 298 Kelvin. They might say is not thermodynamically favorable, which means the same thing at 298. However, at higher temperatures, the reaction becomes spontaneous. Which of the following is true at 298? So first of all, it says it's not spontaneous at 298. So at 298, I should have a positive delta G. So that automatically gets rid of B, D, and E. So let's think about if something becomes spontaneous at higher temperatures, what would be the signs of delta H and delta S? Well, if it's spontaneous at higher temperatures, then they should both be positive. So it would be choice A. So I should know that if they're both positive, it becomes spontaneous at higher temperatures. If they were both negative, it would be spontaneous at lower temperatures. If it was always spontaneous at any temperature, delta H would be negative, delta S would be positive, and vice versa. Okay, let's look at this problem, give it a shot, and then check your work. Ammonium nitrate is added to a flask of distilled water. After mixing, no solid remains, and the flask becomes cold to the touch, which is true. Okay, so if something is dissolving, okay, this is dissolving, it's going from solid to aqueous, all right, the entropy would be increasing, so delta S would be positive. Let's talk about what's happening in terms of delta H. It's telling me the flask becomes cold to the touch. So the reaction must be absorbing heat. So delta H must be positive. And since the reaction actually went forward, it says no solid remains, that must mean it's spontaneous, that this happened without outside intervention. So my delta G would be negative. So that would be choice D. Since the substance dissolved, the reaction is spontaneous, so it's negative delta G. If the flask gets cold to the touch, heat was added or absorbed from the flask, so delta H is positive. And dissolution increases entropy, going from solid to aqueous. Okay, take a moment and try this example. Determine the sign of delta S. I've given you the sign of delta H. And then tell me whether an increase in temperature drives the reactions to the right, to the left, or has no effect. Try it out and then check your work. So for this first one, notice it's an exothermic reaction. Delta H is negative. And I want to know what happens to delta S. So I'm going from 3 moles of gas on the left to 1 mole of gas on the right. So I'm decreasing the number of gases, so entropy would be decreasing. Delta S is negative. Now I see that delta S is negative and delta H is positive. So either logically or just kind of remembering from that chart, if both delta S and delta H are negative, then this is going to be spontaneous at lower temperatures. So an increase in temperature is going to actually make this less thermodynamically favorable. It's actually going to drive it to the left, to the reverse side, to the reactant side, making it not go forward. So again, I wrote drive to the left. The forward reaction is favorable at low temperatures. An increase in temperature, if I'm thinking of my actual reaction, increasing temperature would increase this T delta S term. And this would make it be the unfavorable term in this situation because delta S is negative, which is not favorable. And in turn, it could drive delta G to be positive, thus favoring the reactants. And remember, the reactants are on the left-hand side. So sometimes if they say drive reactions to the right, they're talking about going forward. If they say drive to the left, they're talking about going in reverse, or essentially not going forward. Here's number 2. Here we've got delta H is positive. It's endothermic. And if I notice, I have 3 solids turning into a liquid. So I would assume that entropy is increasing, solid changing to a liquid. So I have delta H is positive, delta S is positive. Well, we said that this is going to become more spontaneous at higher temperatures. So a drive to the right in this situation. The forward reaction is favorable at higher temperatures. An increase in temperature would cause this T delta, the T delta S term to be greater, which in this case now is the favorable term because delta S is positive, and it would in turn make delta G negative, favoring the products. So you can talk about it in terms of this reaction if you wanted to just talk about it in what you know in terms of the positives, 2 positives, high temp, 2 negatives, low temp, however you want to explain that best. Let's talk a little bit more about temperature. So we said just vaguely, we said, okay, positive, positive, favorable at higher temperatures, negative, negative, favorable at lower temperatures. But how can you calculate the point at which that switches, right, from spontaneous to non-spontaneous or vice versa? So first of all, just a reminder that if you have delta H being negative and delta S positive, your favorable conditions all the time, this would be favorable at all temperatures. There's no need to calculate a temperature that it becomes spontaneous because it's spontaneous at any temperature from 0 up to whatever the highest temperature you can think of. Okay, and same with the opposite. If delta H is positive, delta S is negative, there's no need to calculate a temperature that it becomes unfavorable because it will always, always, always be unfavorable no matter what the temperature is. So we never have to calculate a temperature at which these above conditions become favorable or unfavorable because it's true at all the temperatures. However, the other conditions where like delta S and delta H are both positive or they're both negative, we can calculate the temperature at which these reactions become thermodynamically favorable because the direction the reaction proceeds will depend on the temperature. As we said, some things are only favorable at low temperatures, like the negatives, and some are favorable at high temperatures. But what temperature is that? So let's look at an example. At what temperatures is the following process spontaneous or thermodynamically favorable at 1 atm? Okay, so I have this happens to be a phase change. Here's my delta H, here's my delta S. First of all, for this phase change, does it make sense that both delta H and delta S are positive? Well, if I'm going liquid to gas, you can think of it as going up my heating curve. Delta H should be positive, going L to liquid to gas, endothermic, and liquid to gas, increasing the gases should increase the entropy as well, so that does make sense. Anyway, let's calculate the temperature at which this becomes spontaneous. So going back to this equation again, if delta H and delta S are both positive, then this will become favorable at higher temperatures. Okay, so we should try to calculate at what temperature is this going to become spontaneous. So we know the process will be spontaneous and go forward if delta G is negative. So we can calculate at one point this would become negative. Now, if we're putting in less than or equal to, less than or greater than signs, when you put in inequalities into algebra, sometimes it can get a little complicated. So what I like to do is I like to first find the temperature at which delta G is 0, which would again be when we're at equilibrium. So I don't have to worry about inequalities. So that's what I'm going to do. Let's figure out what the temperature would be when delta G is 0. Okay, so if I plug in here, okay, here's 0 for delta G. Let's plug in our delta H and delta S. Notice they have different units of heat, so we have to convert one of them. And rearranging to solve for T, okay, here's my delta H. I converted delta S into kilojoules, okay. And notice my unit is going to end up being Kelvin for temperature because the kilojoules and the moles will cancel out. And I get that my temperature is 333 degrees, and be aware of your unit, it's Kelvin. So this is not the temperature it becomes spontaneous. This is the temperature at which it's in equilibrium. Notice here, liquid to gas, this is a phase change. So actually, this is the boiling point temperature. This is the temperature at which point you'd have liquid and gas in equilibrium, which would only happen at the boiling point. So that's interesting for phase changes. If this was melting, it would be the melting point. Otherwise, you can do this for other reactions. It just wouldn't be a melting or boiling point if it's not a phase change. But this is the temperature at which it's at equilibrium. So how do I know what temperature be spontaneous? Well, since these are both positives, we said they'd be spontaneous at higher temperatures. So basically, you want a temperature that is higher than this value. So the reaction will be spontaneous when T is greater than 333 Kelvin. Notice I didn't put greater than or equal to, because if it's equal to this, it would be at equilibrium. We want it to be spontaneous going forward, not going both forward and reverse. So we want it at 300. We want it greater than 333. Okay, and you have this on the next slide. So again, a question, if delta H is negative and delta S is positive, would there be a need to calculate the temperature at which the reaction is thermodynamically favorable? Nope, it's always favorable. What about the opposite, delta H positive, delta S negative? Would there be a need to calculate the temperature? Nope, it's always unfavorable. And we only have to calculate the temperature if they're both positive or both negative. Now, if you notice, this was a phase change that we were looking at, and I was just talking about this being actually the boiling point temperature. So if I want liquid to gas to occur spontaneously, wouldn't it make sense that I have to be higher than the boiling point? Yeah, look how that works out for phase changes. And if I were lower than the boiling point, would the liquid go forward and change into gas? Nope, it would stay a liquid. So this really, spontaneity, this really makes sense in terms of phase changes. So as I said, let's just recall our phase changes. If we're thinking about whether phase changes are endo or exothermic, I find it really helpful to draw or jot down a little phase heating curve. And remember, anything going up the heating curve, delta H would be positive, solid to liquid to gas. Okay, and delta S would also be positive because solid to liquid to gas increases entropy. And anything where I'm going down, gas to liquid or gas to solid or liquid to solid, delta H would be negative or exothermic, and delta S would be negative because I'd be decreasing the entropy. So like we said, if we change gas to liquid, okay, delta H would be negative and delta S would be negative. I'm going up the graph, so I'm going down the graph, so delta H would be negative. And if I see something like sublimation, okay, solid to gas going up the graph, so delta H would be positive, and solid to gas would also have entropy increasing. So anytime you're talking about phase changes and you need to figure out the delta H, again, I always like to come to the heating curve, draw a little heating curve. So whether phase changes are thermodynamically favorable depend on the temperature that the process is occurring. And that makes total sense. So here we have solid changing to liquid. Okay, going forward, delta S would be positive, solid to liquid, and increasing entropy, increasing dispersal of matter or energy. Delta H would also be positive. This is endothermic. I'm going up the heating curve if I kind of visualize that heating curve. So when above the melting point, okay, if I'm higher than the melting point, high temperature, it would make sense that delta G is negative, that's thermodynamically favorable, that it would go forward. If I'm above the melting point, the ice will melt. Okay, that's why if it snowed and now it's 40 degrees Fahrenheit and the melting or freezing point of water is 32 degrees, I'm going to find all the water as liquid now. So it's product favored and melting would occur. If I'm below the melting point, this forward reaction is not going to occur. It's not going to go solid to liquid. What's going to happen? It's going to stay, it's going to freeze, or it's going to stay as a solid. So delta G would be positive at lower temperatures. Favoring the reverse reaction would be reactant favored, and freezing would occur. Okay, so it makes sense. Positive, positive, favorable at high temperatures. And remember, when at the melting point, delta G is going to be 0 and you're going to be at equilibrium, depending which way you're adding heat, could go forward or reverse. So the phase change is only at equilibrium if at the melting point, and the same thing occurs for boiling or condensation. Okay. And again, as a note, instead of saying positive or negative on the AP exam, often I'll see them write greater than 0 or less than 0. Don't let them throw you off. For some reason, that throws some people off. If delta G is negative or less than 0, it'll be thermodynamically favorable, and that'll always be the case if delta H is less than 0, negative, and delta S is greater than 0. A reaction is thermodynamically unfavorable if delta G is positive or greater than 0. And that's always going to be the case. It's always going to be unfavorable if delta H is positive and delta S is negative. How else can you calculate delta G aside from that, the equation delta G equals delta H minus T delta S? You can actually find tabulated Gibbs free energies of formation. Just like how you've had heats of formation, you can find Gibbs energies of formation. And just like heats of formation, Gibbs free energy of formation is 0 for elements how they are found in nature at their standard states. Remember, the entropies are never 0 for these elements. So just like how we did with heats of formation, you can find delta G by doing the sum of the heats of formation, sum of the Gibbs free energy of formation of the products minus the Gibbs free energy of formation of reactants. And if you're doing textbook problems, you might have to look those up in an appendix. If you were doing a problem on a test or AP, they would be embedded in the problem statement. And this is on the formula sheet, but again, it doesn't remind you about multiplying by the coefficients. Okay, so you can either find delta G by doing this delta G equals delta H minus T delta S, or you can do it this way. So just kind of summarizing that, here's method 1 of calculating delta G that we talked about. Method 2 is actually just like how you can do Hess's law for delta H, you can also do Hess's law for delta G, where if you have steps, you can add up the delta G's of the steps, and that would give you the delta G overall. If there's something you have to flip, you flip the sign of delta G. If you have to multiply by a coefficient, you multiply delta G by that same coefficient. So those same things you can do for delta H, you can do for delta G. And again, as I said, you can get delta G from the Gibbs energies of formation. And if you see an element by itself in standard state, Gibbs free energy is 0.